Welcome back and settle in, because tonight we are going to wonder together about the slow, patient rise of stone. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Imagine, for a moment, that you are drifting high above the planet, looking down at a curve of blue ocean and pale brown land. From this height, the world looks smooth, soft, almost still. Then slowly, your eyes adjust. You begin to see the wrinkles. Long, curving lines of stone rise from the continents like the folds in an old blanket. Some of them run for thousands of miles. Some glow white with snow. Some sit low and rounded, worn down by countless seasons. These are the mountains of the Earth. And they are, in their own quiet way, one of the planet's deepest unsolved riddles. We tend to think of mountains as fixed, permanent, the kind of thing a person might use as a symbol of forever. But that is only because we live such short, bright lives compared to the lives of stones. The mountain is not a still thing. A mountain is a slow event. It is rising or falling or shifting every single moment, only at a pace too patient for our eyes to catch. If you could speed time up, if 1,000,000 years passed in a single breath, you would see the surface of the Earth ripple like the skin of a calm pond. Whole ranges would lift out of flat plains. Others would melt away into hills. The ground itself, the thing we trust to hold still, would flow. And here is the part that researchers still wonder about. We know in broad strokes how mountains form. We have theories, we have measurements. We can watch certain peaks grow taller by a few millimeters each year. But the deeper questions, the ones underneath the textbook answers, remain open. Why do some ranges keep rising long after the forces that made them seem to have stopped? Why do mountains exist at all, on a planet that, given enough time, would prefer to be smooth? What sets the height of the tallest peaks, and why does that height seem to have a quiet limit? Tonight we will sit with those questions. We will not rush to answer them. We will let the mystery breathe. Picture the Himalayas at dawn. The light spreads slowly across the snow, turning it pink, then gold, then a soft, clean white. The peaks are so high that the air at their summits is too thin for most living things. And yet, if you could chip a piece of stone from near the top of Everest and look closely, you might find tiny fossils. Fossils of sea creatures. Shells that once lay on the floor of a warm, shallow ocean. That ocean is gone. The shells are at the top of the world. Something lifted them there. Now picture the Appalachians of eastern North America, soft and green and rounded, draped in summer mist. These mountains were once as sharp and tall as the Himalayas are today, maybe taller. Time has worn them down to gentle ridges, and the rivers that drain them carry the old stone, grain by grain, back to the sea. They are dying ranges, beautiful in their tiredness. And then picture the Andes, running like a long spine down the western edge of South America, with volcanoes still steaming at their crests. These are mountains still being born. The earth beneath them is still pushing. 3 ranges, 3 different stages of a story so long that no single human being could ever watch it from beginning to end. What we are really looking at, when we look at any mountain, is a frozen moment in a process that began before our species existed and will continue long after we are gone. The peaks we know by name are simply the ones that happen to be standing during the brief flicker of human history. Before them were other mountains, lost to erosion, their bones scattered into sand. After them will be mountains we will never see. The open question, the one we will keep returning to tonight, is this. We can describe what mountains do. We can measure how fast they rise. But the full story of why and how the Earth keeps building these great wrinkles in its skin, the deep, complete answer, still hides somewhere beneath our feet. So let your shoulders soften, let your breathing slow, and let us begin gently with the wandering plates beneath us. To understand how mountains rise, we have to begin with something strange and almost unbelievable. The ground beneath you is moving, not quickly, not in any way you can feel, but the solid earth under your feet is sliding very slowly across the surface of the planet. It has been doing this for billions of years, and it will keep doing it long after we are gone. The outer shell of the earth is not one solid piece. It is broken into huge slabs of rock called tectonic plates. These plates float on a deeper layer of hot, slow-moving stone. Picture cold crackers resting on a thick pot of warm honey. The crackers do not melt, they just drift gently as the honey churns below them. There are about 15 large plates and many smaller ones. Together, they cover the entire surface of the Earth, both the land and the seafloor. Some plates carry whole continents on their backs, others carry only ocean. The plate beneath the Pacific Ocean is the largest of all. It is so wide that it would take a passenger jet nearly 15 hours to fly from one edge to the other. The plates are thick, but not as thick as you might guess. Under the oceans, a plate is usually around 5 miles deep. Under the continents, it can reach about 25 miles and a bit more under big mountain ranges. That sounds like a lot, but compared to the whole Earth, it is almost nothing. If our planet were the size of an apple, the plates would be thinner than the apple's skin. Everything we know, every forest, every city, every mountain, rides on that thin skin. Below the plates is a layer called the mantle. The mantle is not liquid in the way lava is. It is solid rock, but so hot and under such pressure that it flows very slowly, like warm clay being kneaded by invisible hands. This soft, churning rock is what carries the plates along. Heat from deep inside the Earth rises through the mantle, cools near the top, and sinks again. That slow turning is the engine that moves the world. How fast do the plates actually travel? About as fast as your fingernails grow. Roughly 1 to 4 inches a year. That is slower than a snail by a long stretch, but give it time and that pace becomes powerful. Over a single human lifetime, a plate may shift only a few feet. Over 1 million years, it can move dozens of miles. Over 100 million years, it can carry an entire continent across an ocean. This idea is fairly new in the long story of science. The theory of plate tectonics only took its modern shape in the 1960s. Before that, mountains were a puzzle that no one could fully solve. People could see the folded rock, they could see the great peaks. But they could not agree on what pushed the stone upward in the first place. Some thought the Earth was shrinking and wrinkling like a drying apple. Others thought the crust rose and sank in slow, mysterious tides. The truth, as we understand it now, turned out to be stranger and more elegant than any of those guesses. Still, even today, much remains uncertain. We know the plates move. We can measure them with satellites that track tiny shifts in the ground from orbit. We can map their edges by listening to earthquakes, but the deep machinery, the exact way heat rises and falls through the mantle, is still being worked out. There are competing models. Some researchers think the flow is mostly driven by sinking cold slabs at the edges of plates. Others think rising plumes of hot rock from very deep in the mantle play a bigger role. The honest answer is that both probably matter in ways we have not yet fully measured. What we can say with confidence is this: where two plates meet, something has to give. They may crash into each other. They may slide past each other. They may pull apart, opening cracks that fill with molten rock. And in those meeting places, the great mountains of the world are born, lifted out of the slow grinding of stone against stone. So tonight, as you lie still, remember that the ground holding you up is not still at all. It is drifting, breathing, turning over itself in patterns older than memory. Somewhere right now, two enormous slabs of rock are pressing against each other, raising a peak by a fraction of an inch. We are only beginning to understand the dance, and the dance has been going on for a very, very long time. Imagine for a moment two great rafts of stone drifting across the warm back of the earth. They move slower than your fingernails grow, yet across millions of years they cross oceans, they wander, they turn, and sometimes, very rarely from our short human view, they meet. When two continents finally touch, something quiet and enormous begins. The ground does not leap into the sky overnight. It does not crack open in some sudden show. Instead, the rock begins to crumple, fold by fold, the way a thick rug crumples when you push two ends together across a wooden floor. This crumpling is the birth of many of the great mountain ranges we know. To understand how it begins, picture the edge of one continent slipping under the edge of another. This slow tucking is called subduction, when one plate dives beneath its neighbor and sinks into the hot rock below. For long ages, this works smoothly enough. The ocean floor between two continents slides down into the depths, vanishing into the warm interior of the earth like a long ribbon being pulled into a slow fire. The trouble, if you can call it that, comes when the ocean between the two continents finally runs out. The seabed has all been swallowed. Now the two continents themselves arrive at the meeting place, and continents do not like to sink. They are made of lighter rock, thick and stubborn, and they refuse to slide easily into the dark below. So instead, they push, they press, they grind. The land between them has nowhere to go but up. This is, in the broadest strokes, how many of the world's tallest mountains were born. The Alps rose when Africa drifted gently northward into Europe. The Himalayas rose when the wandering piece of land we now call India crashed slowly into the southern edge of Asia. The Appalachians, far older and softer now, were born from older meetings still, long before any human eye could have seen them. But here is where the calm wonder of the story deepens. We know the broad shape of how this happens. We can measure the plates. We can map the folds. And yet many of the deepest details remain open questions. How exactly does a slab of cold ocean rock break away once the diving has stopped? How much of the lifting comes from pure pushing, and how much comes from the rock itself growing thicker as it crumples? How does the deep root of the mountain, hidden many miles below the surface, decide how high the peaks above can rise? These are real questions that geologists still discuss in quiet papers and long conferences. One idea is that mountains rise mostly because the crust is being squeezed thicker, like a stack of soft clay pressed from both sides. Another idea is that much of the height comes from the buoyancy of that thick root, floating on the denser rock below, the way a thick piece of wood floats higher than a thin one. Both ideas seem to play a part. The exact share remains a matter of careful debate. The time involved is hard for the human mind to hold. A continent moving at the pace of a growing fingernail will travel about a meter in 30 years. To close an ocean 1,000 miles wide takes tens of millions of years. The mountains that follow may take tens of millions more to reach their full height. By the time a range stands tall enough to wear a crown of snow, the species that watched its birth are long gone, and new ones have arrived to wander its valleys. The conditions must also be just so. The plates must be moving in the right directions, with enough force for long enough, against rock strong enough to fold rather than simply break apart. If the angle is wrong, you get something different, a long zone of cracks, perhaps, or a wide basin instead of a ridge. The Earth seems to know many ways to behave when its plates meet, and we are still learning to read its choices. Stand for a moment in your mind on a high pass in any of these ranges. The wind is cold. The stone underfoot is the floor of an old sea lifted miles into the sky by a slow collision that began before the first fish swam. You can rest your hand on a layer of rock that was once mud at the bottom of warm water. Now it sits among the clouds. How exactly it got there in every fine detail is something we are still piecing together. For tonight, it is enough to picture the slow meeting of continents and the patient rise of stone. Of all the mountains on Earth, none holds a deeper question than the Himalayas. They rise along the northern edge of India in a long curving wall of stone and ice. Some of their peaks climb more than 8 kilometers into the sky. The air at the top is thin and cold, and the rock there once lay at the bottom of a warm sea. That single strange fact has puzzled people for a very long time. The Himalayas are made of many things, and each thing carries its own quiet story. There is granite, a hard speckled rock born deep underground from cooling magma. There is gneiss, with its dark and light bands swirled like slow smoke. There is schist, which shines softly when the light catches the tiny flakes of mica inside it. And high up, near the summits, there is limestone, a pale gray rock formed from the shells of sea creatures that lived millions of years ago. Climbers have found fossils of ancient ocean life near the top of Everest. The stone remembers a sea that is no longer there. To understand how that sea ended up in the sky, we have to look at what the mountains are built from at the smallest scale. Every rock is a mixture of minerals, and every mineral is a mixture of elements. Silicon and oxygen are the most common. They join together in long, quiet patterns to make quartz, feldspar, and the other building blocks of the crust. There is also aluminum, iron, calcium, magnesium, and potassium woven through the stone in different amounts. These are the same elements that make up most of the dry land everywhere on Earth. What is gentle to remember as you listen is that none of these elements were made here. The silicon in a grain of Himalayan sand, the iron that gives some of the rock its rusty color, the calcium in the old seashells now lifted into thin mountain air. All of it was forged long ago inside stars. When those stars grew old and shed their outer layers, they scattered these elements into the dark. Our planet later gathered some of that dust and pressed it into a world. Every mountain, in a way, is starlight that has slowed down and turned solid. Even the water that helped shape the Himalayas may have a distant origin. The rivers that carve the deep gorges, the glaciers that grind the high valleys, the snow that falls so softly on the slopes, all of it is water. And one open question in science is where Earth's water first came from. One idea is that much of it came from icy comets that struck the young planet. Another idea is that the water was already mixed into the dust that formed Earth in the first place. Researchers are still measuring the chemistry of comet ice and ocean water, trying to see if they match. The question is not yet settled. The Himalayas themselves carry their own unsolved riddle. We know they began rising when the Indian plate pushed into the Asian plate about 50 million years ago. We know the collision is still happening, and the mountains are still being lifted, slowly, every year. But how high they were at different points in their past, how quickly they rose, and how much they have worn down along the way, these are questions geologists still argue about. Some studies of ancient leaf fossils suggest parts of the range were already very tall long ago. Other studies suggest the great heights came later. The stone gives hints, but no clear answer. There is also the puzzle of what lies beneath. The Himalayas have deep roots of rock pressing down into the mantle, the hot, slow layer under the crust. Exactly how those roots behave, how they hold the weight of the peaks above, and how they may shift over millions of years is still being studied. The mountain we see is only the top of something much larger and quieter, hidden from view. So when you picture the Himalayas tonight, picture them as a meeting place. Starlight gathered into dust, dust pressed into stone, stone lifted by the slow push of continents. Sea floors raised into the sky, comets perhaps leaving water that became glaciers. Every element in those peaks has traveled a long way to be there, and the mountain itself is still moving, still changing, still keeping some of its secrets folded inside its layers. The Himalayas are not finished. The story they are telling is one we are only beginning to read, line by patient line, in the language of the rock. Not every mountain rises from the slow press of one plate against another. Some are born from fire. Deep below the surface, far beneath our feet, the rock is not the cold gray stone we know. It is hot. In some places, it is hot enough to melt. When that melted rock, called magma, finds a path upward, it can build a mountain from the inside out, layer by glowing layer, over thousands or millions of years. These are the volcanic mountains, and the forces that shape them are different from the folding and crumpling we spoke of before. Here, the work is done by heat, by pressure, and by the strange behavior of melted stone trying to reach the open air. Picture a slow current of hot rock deep in the mantle, that thick layer of warm stone beneath the crust. It rises, very gently, the way warm water rises in a pot before it boils. When it reaches the underside of the crust, it can pool there, melting the rock above it and gathering into a hidden chamber. Inside that chamber, pressure builds. Gas dissolves into the magma the way bubbles hide inside a sealed bottle, and when a crack opens above, the magma climbs. Some volcanic mountains grow quietly. They ooze thin, runny lava that spreads out in wide, gentle slopes. The Hawaiian Islands, rising from the floor of the Pacific, are built this way. Layer after layer of cooled lava stacks up over hundreds of thousands of years until a mountain emerges from the sea. From the ocean floor to the summit, some of these peaks are taller than Everest, though most of their height is hidden beneath the waves. Other volcanic mountains grow with sudden, restless energy. They build their slopes from thick, sticky lava and from showers of ash and stone. These are the steep, classic cones we picture when we hear the word volcano. The pressure inside them rises slowly, then releases in a brief burst, and the mountain adds a new layer of itself to the world. Mount Fuji in Japan, the slopes of the Andes, the quiet shape of Mount Shasta in California, all of them are stacks of old eruptions, frozen in stone. The force behind all of this is heat. The inside of the Earth is still warm from its birth, more than 4 billion years ago, and warm from the slow decay of natural elements deep within. That heat has to go somewhere. It rises very slowly toward the surface. In some places, it finds its way out through long cracks where plates pull apart. In other places, it punches up through the middle of a plate in a column of hot rock called a plume. These plumes are one of the great open questions in the study of mountains. We can see what they do. We can map the chains of volcanoes they seem to leave behind, like footprints across the seafloor. But we cannot directly see them. They lie hundreds of miles down, hidden inside the dark mantle. Some researchers believe these plumes reach all the way to the boundary with the Earth's outer core. Others wonder if they are shallower, born in the middle layers of the mantle. The evidence is gathered through faint signals, the way earthquake waves slow down when they pass through hotter rock, and those signals are still being read. There is also the quiet question of why some volcanoes form where they do. Most sit along the edges of plates, where one slab of crust slides beneath another and melts. That part we understand fairly well. But some, like the volcanoes that built Hawaii or Yellowstone, sit far from any plate edge. They appear to rise from a fixed point of heat, while the plate above them drifts slowly past. One theory calls these points hotspots. Another suggests they might be something else entirely, perhaps shallow pockets of melt, perhaps cracks in the plate above that let heat escape. The debate continues, gently, in quiet laboratories and on long ocean voyages. What we do know is that fire-born mountains are still being built tonight. Somewhere in the dark beneath the Pacific, lava is touching cold seawater and turning instantly to glassy stone. Somewhere, a slope is rising by a fraction of an inch. Somewhere, a chamber of magma is gathering itself in patience, waiting for a path upward that may not open for another 1,000 years. The forces are gentle and enormous at once, heat that has been traveling outward for billions of years. Pressure that builds across centuries, stone that turns to liquid and then to stone again. And from these slow, hidden movements, a mountain rises, one quiet layer at a time, into the open sky. To understand mountains, it helps to shrink the Earth down to something you can hold. Imagine our planet as a smooth apple resting in your hand. At that scale, Every mountain on Earth, even the tallest, would be thinner than the skin of that apple. The whole rumpled crust, with its peaks and valleys and ridges, would feel almost smooth under your thumb. The Earth is so vast and its surface so thin that the great ranges we admire are little more than wrinkles on a moving fruit. Yet from where we stand, those wrinkles are everything. They tower above us. They feed our rivers. They cradle the clouds. Scale is a strange thing on this planet. What feels enormous from below becomes a faint texture from above. Try another picture. If you shrank the Earth to the size of a basketball, the highest mountain on land would rise only about 1/3 of a millimeter from the surface. That is thinner than a sheet of paper. The deepest ocean trench on that same ball would be a scratch barely deeper than the seams. All of human history, all of our cities and farms and footprints would live inside that paper-thin shell. Now stretch the picture outward. The crust of the Earth, where mountains live, is between 5 and 70 kilometers thick. Beneath the oceans, it is thinner. Beneath the continents, it swells. Under the great ranges, it thickens even more, like dough pressed into a fold. If you could slice the planet open and look at it edge-on, the crust would be the faintest rind, and the mountains would be small bumps along that rind. The numbers feel almost unfair. Mount Everest stands nearly 9 kilometers above sea level. That sounds enormous, and for a human body, it is. The air there is too thin to breathe for long. The cold there can freeze skin in minutes. Yet compared to the radius of the Earth, which is over 6,300 kilometers, Everest is a freckle. If you walked away from the planet and looked back, you would not see it. The Earth, from far away, looks perfectly round. Time stretches the scale even further. A mountain range like the Himalayas has been rising for roughly 50 million years. That is hard to feel in the body. Try this. If you compress the entire history of the Himalayas into a single day, then 1 second of that day would equal about 578 years. A human lifetime in that scaled day would pass in less than the blink of an eye. Whole civilizations would rise and fall between 2 heartbeats of the mountain. And the rate of growth is gentle beyond imagining. The Himalayas push upward by only about 1 centimeter each year on average. That is roughly the thickness of a pencil. In 100 years, a meter. In 10,000 years, the height of a tall building, if erosion did not steal much of it back. The mountain you see today is the patient sum of countless tiny lifts, each one too small to notice, stacked across a span of time the human mind cannot truly hold. The width of the Great Ranges is its own kind of vastness. The Andes run for about 7,000 kilometers along the western edge of South America. If you set out walking at a steady pace, it would take you more than a year to travel their length without stopping. The Rockies stretch across thousands of kilometers as well. The Alps, smaller in scale, still cross 8 different countries. These are not single peaks. They are long welts in the skin of the planet, raised by the slow pressing of one slab of crust against another. And still, with all this size, much remains unclear. Researchers continue to wonder why some folds in the crust rise into tall, sharp ranges, while others settle into low, rolling hills. The math of how stone bends, how heat softens it, how water weakens it, is still being worked out. Some models suggest the strength of the rock matters most. Other models point to the speed of the colliding plates or the thickness of the crust beneath. The question stays open. What we can say is this: the Earth is a great round body, mostly hidden from our eyes, and the mountains we love are only the faintest rumples on its outer skin. They are huge to us. They are tiny to the planet. They are old beyond our reckoning, and they grow at the pace of a fingernail. Hold that quiet contradiction for a moment and let it carry you a little further towards sleep. Imagine for a slow moment that you are floating just above a dry valley somewhere in the high country of the world. The sun is low. The light is soft and gold. Below you, the land is split by a long, thin line that runs for miles across the floor of the valley. It looks almost like a scar. In some places, it is a low wall of pale rock. In other places, it is a shallow trench, half filled with dust and tumbled stones. This line is a fault, and faults, in their quiet way, are some of the most patient builders of mountains on Earth. A fault is simply a crack in the rocky outer skin of the planet, a place where two slabs of stone have slipped past each other. Some faults are tiny, some run for hundreds of miles. From the air, the long ones look like seams in old leather, stitched into the surface of the land. They cut across deserts, they climb into hills, they vanish under rivers and reappear on the far bank, still tracing the same slow line. If you walked along one, you would see strange things in the rock. Layers that should match up on either side of the crack do not. A bright orange band of stone sits high on one wall and low on the other. A vein of white quartz ends suddenly, then picks up again 20 feet away in the wrong direction. These mismatched layers are the fingerprints of movement. Stone has shifted here, not all at once and not quickly, but in countless small jumps over many lifetimes of the Earth. In some valleys, you can stand at the foot of a steep, fresh-looking cliff that rises straight from the flat ground. The cliff face is pale and raw. The land at its base is gentle and dotted with sagebrush. That cliff is called a fault scarp. It is the edge of a block of land that has been pushed upward, or the edge of one that has dropped down. Either way, the difference between the high side and the low side is the small beginning of a mountain. Stack enough of these movements over millions of years, and you grow a range. The Sierra Nevada in the western part of North America is thought to be a mountain block of this kind. One enormous slab of crust has slowly tilted, lifting its eastern edge high into the sky, while its western edge sinks gently away. From far above, the range looks like a great stone door, slowly opening. The sharp eastern wall faces a deep valley. The long, sloping back fades into rolling foothills. What you are seeing, in a sense, is a single very slow motion frozen partway through. In other parts of the world, faults do not lift the land so much as slide it sideways. Two great blocks grind past each other, scraping along for inch after inch over the centuries. Where this happens, the surface develops strange features. Streams take sudden right-angle bends, ridges step out of line with their neighbors, small ponds form in low spots along the crack. From above, the land looks gently rearranged, as if a careful hand had nudged it out of place. Researchers still debate how much of a mountain's height comes from this kind of patient fault movement, and how much comes from deeper forces below. One idea is that faults are mainly the surface expression of motion happening far underground, where hot rock flows like thick syrup. Another idea is that the faults themselves do much of the lifting, with each small slip adding a tiny bit of new elevation. Most likely, both are true in different places in different amounts. The full recipe is still being worked out. What is clear is that faults are slow. A fast fault might move an inch or two in a year. A slow one might creep along at the speed your fingernails grow. And yet, given enough time, this gentle shifting builds entire ranges. The cliffs of the Teton Range in Wyoming, sharp and dramatic against the sky, are thought to have risen this way, fault movement by fault movement, over millions of quiet years. If you stood on that valley floor at dusk, looking up at such a wall of stone, you would not feel any motion. The ground would be still, the air would be cool, a few birds might pass overhead, and yet beneath your feet the slow arithmetic of the fault would still be working, a grain of pressure here, a whisper of slip there, the mountain growing by an amount too small to measure in a single human life, but more than enough over the long memory of the earth to lift stone into the clouds. When we look at a mountain, we see only a small part of what it really is. The peak, the ridges, the slopes covered in trees or snow, these are just the top of something far larger. Beneath every great mountain range, hidden deep in the earth, there is a kind of mirror image of the peak above. Geologists call it the root, and the root may be many times larger than the mountain we can see. Think of an iceberg floating in a cold sea. Only a small part of it shows above the water. Most of the ice hangs down below, quiet and hidden, holding the rest up. Mountains work in a similar way. The crust of the earth floats on the soft, slow-moving rock beneath it. Where the crust is thick, it sinks deeper into that soft layer, and it also rises higher into the sky. So under a tall mountain, the crust pushes downward like a heavy keel. This idea has a name. It is called isostasy, which simply means a kind of balance. The crust floats, and the mountains balance themselves with their own hidden weight. Under the Himalayas, the crust may reach down nearly 70 kilometers. That is more than 7 times the height of the tallest peak above. A vast cold wedge of stone, pressed into the warmer rock below, holding the world's highest summits in place. We cannot dig down to see these roots. No drill has ever reached them. The deepest hole humans have ever made goes only about 12 kilometers into the crust, and it took decades to reach that depth. Everything we know about mountain roots comes from listening. When earthquakes happen, they send waves of energy through the earth. Those waves travel at different speeds through different kinds of rock. By measuring how long they take to arrive at distant stations, scientists can sketch a rough picture of what lies below. It is a little like tapping a melon to guess what is inside. These soundings have shown us strange things. The roots of mountains are not simple. They bend, they twist. Sometimes they seem to break off and sink away into the hotter rock beneath, like wax dripping from a candle. This idea is called delamination. One theory holds that when a mountain's root grows too cold and heavy, it can peel loose and fall slowly into the mantle below. When that happens, the mountain above may suddenly rise, lighter without its anchor. Some researchers wonder if this has shaped ranges like the Sierra Nevada in western North America. Others are not convinced. The evidence is faint, gathered from echoes deep in the dark. There is also the question of what the roots are made of. Near the surface, mountain rock is familiar, granite nice, the patient stones we can hold in our hands. Deeper down, the pressure changes everything. Common minerals fold themselves into denser forms. Garnet appears. Strange high-pressure crystals grow that we almost never see at the surface. A few have been brought up by accident, carried in tiny grains by volcanic eruptions or by ancient collisions that briefly turned the deep crust inside out. Each fragment is like a single page torn from a much longer book. The deepest parts of these roots sit at temperatures hot enough to soften steel, yet the rock there does not melt. The crushing pressure keeps it solid, though it can flow very slowly, like cold honey given 1,000 years to move. This slow flow may be one of the quiet forces that shapes mountains over time. As the root creeps and shifts, the surface above may rise or sink by amounts too small to feel in a single lifetime. There is much we still do not understand. We do not know exactly how mountain roots form in the first place. Do they grow slowly, layer by layer, as collisions push more crust downward? Or do they form in sudden pulses when great slabs jam together and bend? We do not know how long a root can last before it breaks away. We do not know whether some old mountain ranges still have their roots hidden under flat plains, waiting to lift the land again one day. For now, the roots remain mostly invisible to us. We sketch them in faint lines, drawn from the whispers of distant earthquakes. Beneath every familiar peak, there is this other, larger mountain pointing down into the dark, a quiet twin made of pressure and patience, holding up the sky without ever being seen. And as you settle a little deeper into the quiet of this hour, perhaps imagine that hidden weight below the world's high places, balanced so gently, so slowly, for so long. Mountains rise and mountains fall. That simple sentence holds one of the deepest rhythms of our planet. The peaks we know today, the bright young giants of the Andes and the Alps and the Himalayas, are only the latest verse in a song the Earth has been singing for billions of years. Long before them, other ranges stood just as tall. Other summits caught the morning light. And those mountains are gone now, worn down to soft hills and quiet plains, their bones still hidden beneath the grass. This is the riddle of ancient ranges. The Earth seems to build mountains in slow pulses, raising them up over tens of millions of years, then letting wind and water and ice grind them back down. The cycle takes so long that no single life, no single civilization, can watch even one full turn of the wheel. We only catch glimpses. We see young mountains still climbing. We see middle-aged mountains holding their shape. And we see the worn stumps of ancient ranges, the last quiet witnesses of summits that vanished long ago. The Appalachians of eastern North America are one of these witnesses. Today they are gentle, rounded, green in summer and gold in autumn. But the rocks tell a different story. Once, hundreds of millions of years ago, those mountains may have stood as tall as the Himalayas do now. Their peaks were jagged, their valleys were deep. Then time went to work. Rain fell season after season, for a span the human mind can barely hold. Rivers carried the stone away, grain by grain, to distant seas. What remains is only the soft shoulder of something that was once enormous. The Scottish Highlands tell a similar tale, and so do the Ural Mountains that divide Europe from Asia. These ranges are old, far older than the young giants we admire today. They are the quiet elders of the mountain world, still standing but no longer reaching. And the puzzle is this: we do not fully understand the rhythm. We do not know exactly how long a mountain range can live, or what truly decides when it begins to fall. One idea is that mountains have a kind of natural lifespan, governed by the balance between uplift from below and erosion from above. As long as the plates keep pushing, the peaks keep rising. When the pushing slows or stops, erosion wins. Some researchers wonder if this balance is steady, almost predictable, like the long breath of the earth. Others suspect the cycles are messier, full of starts and stops, with mountains sometimes pausing for hundreds of millions of years before fading. There is also the strange question of the roots. When a mountain is worn down at the surface, its deep root in the mantle slowly rises in response, like a ship lightening its load. This rebound can keep a range standing far longer than erosion alone would allow. Some old mountains may be held up not by ongoing collision, but by the slow, patient lift of their own buried foundations. How long that lift can continue, no one is quite sure. The fossil record adds another layer to the riddle. Tiny minerals locked inside ancient stones can sometimes reveal how high a vanished mountain once stood. By studying the chemistry of these grains, researchers can guess at the altitude of peaks that crumbled long before the first dinosaurs walked. Some of these lost ranges may have been as grand as anything we see today, and yet the evidence is fragmentary. The Earth keeps most of its old mountain stories to itself. There is a gentle thought in all of this. Every range we love now is on its way to becoming a memory. The Himalayas will not always touch the clouds. The Alps will soften. The Rockies will round and fade. And somewhere, in some quiet corner of the planet, a new collision is already beginning, slow as the drift of continents, raising the first low ridges of a range that will rule the skyline 100 million years from now. We will never see it, our great-grandchildren will never see it, but the rhythm continues, indifferent and patient, building and unbuilding, breath after long breath. So the riddle is not whether mountains rise and fall. They do. The riddle is the shape of the cycle. How long does a peak get to stand? What sets the pace of its undoing? Whether the Earth has a steady pulse, or many overlapping pulses, or no true rhythm at all. The rocks know. They have known for ages beyond counting, and they tell us only a little at a time, in fragments of stone and slivers of crystal, while the wind keeps doing its slow, quiet work above. High in the Himalayas, on cold gray slopes far above any living sea, there are stones that hold the shapes of ancient shells. Tiny spiral creatures pressed into rock, resting at altitudes where the air is thin and the wind never warms. These small fossils have a quiet story to tell. They lived long ago on the floor of a warm ocean, and somehow over time, that ocean floor became the roof of the world. It is one of the strangest neighborhoods on Earth. The sea, lying low and heavy, the mountain standing tall and proud. They seem like opposites. Yet again and again, in range after range, geologists find that the highest stones once rested in salt water. The summit and the seafloor are old neighbors, trading places across vast stretches of time. The story of how this happens begins in the slow drift of the plates. A piece of ocean floor, soft with mud and full of shells, lies between two continents that are moving toward each other. As they close in, the ocean between them shrinks. The water has nowhere to go but away. The seafloor crumples. Layers of mud, sand, and limestone get squeezed upward, folded like a thick blanket pushed against a wall. What was once flat and wet becomes steep and dry. The shells come along for the ride. The Alps were born this way in part. So were the Zagros Mountains of Iran and the long curve of the Apennines down the spine of Italy. Each range holds marine fossils tucked into its higher rocks. Sea lilies, ancient corals, small swimming creatures pressed flat by the weight of stone. They sit far above the modern sea, in places where no tide will ever reach them again. The mystery is not just that this happens, it is how completely the sea can disappear. Whole oceans have closed over the long history of the planet. One of them, called Tethys by geologists, once stretched between the great northern lands and the great southern lands. Tethys held warm, shallow waters full of life. Today, almost nothing remains of it. Its floor has been folded into the Alps, the Caucasus, the Pamirs, the Himalayas, a whole sea pressed into mountains. The maps of that lost ocean must be drawn from clues alone, from the patterns of fossils and the chemistry of rocks scattered across many countries. This raises a soft and lingering question. How many oceans have come and gone in Earth's long memory? We know of several. There are hints of others, older still, whose floors may now rest in ranges so worn down that we no longer recognize them as mountains at all. Some researchers wonder whether certain low hills in old continents are the last quiet remains of seas that closed before complex life even began. The evidence is faint. The rocks have been changed, heated, twisted. They no longer speak clearly. The question stays open. There is another neighbor in this story, and it is the salt itself. When a sea dries before it is lifted, it can leave thick beds of salt behind. Those beds get buried, then folded into mountains along with everything else. Hidden inside some ranges, far from any modern coast, there are layers of ancient sea salt waiting in the dark. Miners have found them in the foothills of the Himalayas, in the Alps, in the mountains of Poland. Each pinch of that salt is a tiny memory of a vanished ocean. The interaction between sea and summit also runs the other way. Mountains, once raised, send their broken pieces back toward the ocean. Rivers carry sand and silt down from the peaks. That sediment settles on the seafloor, sometimes for hundreds of millions of years. If the plates shift again, those layers may rise once more, lifted into a new range built partly from the bones of the old one. The cycle turns slowly. A grain of quartz might travel from a Himalayan ridge to the Bay of Bengal, then wait in darkness until the next great collision lifts it skyward again. No one fully understands the rhythm of these exchanges. We can describe the basic motions, but the timing is uncertain. Why do some seas close quickly while others linger for hundreds of millions of years? Why do some ocean floors fold into towering ranges while others slide down into the deep mantle and vanish without a trace? The answers depend on heat, on the strength of the plates, on forces we still measure imperfectly. For tonight, it is enough to picture the small spiral shell resting in cold stone far above any living tide. It was a neighbor of fish once. Now it is a neighbor of clouds, and the sea that held it is gone. Mountains rise, that much we know. But while they rise, something else is always at work, doing the opposite, quietly and without rest. Erosion, the soft hand of wind, water, and ice that touches every stone and asks it, gently, to come apart. It seems strange that something so gentle could undo something so vast. A single raindrop falling on granite seems harmless. A breath of wind across a ridge seems like nothing at all. Yet over millions of years, these tiny touches can lower a mountain by miles. The peaks we walk among today are only what is left after this slow, patient sculpting. The mountain you see is the part that erosion has not yet taken. Consider some of the extremes. In parts of the eastern Himalayas, where rivers like the Tsangpo carve through the rock, erosion may strip away as much as a centimeter of stone every year. That sounds small, but spread across a whole range, across thousands of square miles, it becomes an astonishing amount of rock. Whole mountains, ground into sand and silt, carried out to sea. The rivers there run brown with the bodies of former peaks. At the other end of the spectrum sit the dry, cold deserts of Central Asia, or the frozen plateaus of Antarctica, where erosion crawls so slowly it almost stops. In these places, surfaces can sit nearly unchanged for tens of millions of years. A stone laid down in the age of the dinosaurs may still rest on the same plane, barely touched. The same wind that polishes a Himalayan ridge in a season may take an eon to do the same work in the dry valleys of the south. Researchers measure erosion in many ways. They study the tiny grains of sediment carried by rivers. They count rare atoms that form in rock when cosmic rays strike the surface. The more of these atoms a stone holds, the longer it has sat in the open air. By reading these atomic clocks, geologists can tell how fast a slope is wearing down, sometimes within a few hundred years. It is patient, careful work, like reading the lines on an old face. One of the strangest extremes is the way climate and erosion seem to dance together. In the wettest, rainiest parts of a range, where monsoon storms drench the slopes, the rock comes down fastest. In the driest, calmest places, it lingers. So mountains, in a sense, are shaped as much by weather as by the deep forces that push them up. The question that remains open is how tightly these things are linked. Some researchers wonder if heavy rain on one side of a range can actually pull more rock upward from below by lightening the load. Others are not so sure. The evidence is mixed and the math is hard. There are stranger extremes still. Certain rivers, given enough time, cut through rising mountains faster than the mountains can rise. The Indus and the Tsangpo are thought to have carved their canyons this way, slicing down through stone that was lifting beneath them. The result is some of the deepest gorges on Earth, places where the walls climb 3 miles or more from the river to the ridge. Standing at the bottom of such a canyon, a person feels very small, and the river feels very old. In other places, erosion has done the opposite of what you might expect. It has revealed mountains that were once hidden, great blocks of rock that formed deep underground under heat and pressure, have been lifted toward the surface and then uncovered, one slow layer at a time. The polished domes of certain ranges are old roots, exposed at last. The mountain we see is not the mountain that was built. It is the inside of a mountain, slowly turned out into the light. What no one has fully solved is the balance between these two great forces. How much of a mountain's shape comes from the push below, and how much from the wearing away above? The Andes, the Alps, the Rockies, each range tells the story a little differently. In some, erosion seems to be winning. In others, the uplift still has the upper hand. And in some, the two seem locked in a long, quiet draw, neither gaining much ground over a million years. So tonight, as you settle further into the calm, picture a single drop of water falling on a high stone ridge. It runs a small path down the rock and is gone. Then picture that drop multiplied across every storm, every season, every age. The mountain stands, the mountain falls, and no one yet knows the full shape of that endless, gentle argument between stone and sky. High in the mountains, where the air thins and the cold becomes a steady companion, there are sculptors at work. They move so slowly that we cannot see them move at all. They are made of ice, and they have been shaping the peaks for far longer than any of us can imagine. Glaciers are patient. They have time the way mountains have time. A glacier is a river of ice. It begins as snow, falling softly over many winters, layer upon layer, until the weight of the upper snow presses the lower snow into something harder. First, it becomes a grainy substance, the texture of coarse sugar. Then, deeper still, it becomes solid ice, but ice unlike the kind in your freezer. This ice has been squeezed so hard that the air bubbles inside it are tiny and bright. When light passes through it, the ice glows a soft blue, the color of a deep winter sky just before dusk. Once the ice grows thick enough, it begins to flow. This is one of the quiet wonders of the natural world. Solid ice, under its own great weight, behaves almost like a slow liquid. It creeps downhill at the pace of fingernails growing. A glacier may move only a few inches in a day. Some move faster, some slower, but they all move, and as they move, they carve. The shapes they leave behind are some of the most beautiful in any mountain range. A valley cut by a river is narrow at the bottom, shaped like the letter V. A valley cut by a glacier is wide and rounded at the bottom, shaped like the letter U when you stand in such a valley and look up at the smooth walls rising on either side. You are standing inside a sculpture that took tens of thousands of years to finish. Glaciers carve sharp peaks too. When ice gathers on 3 or 4 sides of a mountain and grinds away at it slowly from each direction, what remains in the middle is a tall, pointed summit, almost like a stone tooth. Geologists call these horns. The most famous example in Europe rises above a Swiss village, but you can find these horn-shaped peaks in many ranges around the world. Each one is the leftover heart of a mountain that the ice could not quite finish eating. Look closely at the rocks at the base of a glacier, and you may see long, fine scratches running in parallel lines. These are called striations. They were made by smaller stones held tight in the underside of the ice, dragged across the bedrock like the teeth of a slow file. Scientists love these scratches. They tell us which way the ice was flowing, even long after the ice itself has melted away. A striation can record the direction of a glacier that vanished 20,000 years ago. There are smaller marks too, almost invisible unless you kneel down and look. Crescent-shaped chips in the rock, no bigger than a fingernail. Tiny polished surfaces where the ice rubbed the stone smooth as glass. In the right light, the polished rock shines softly, as if someone had waxed it. glaciers leave gifts behind as well. As they melt, they drop everything they were carrying. Boulders the size of houses sit in fields where they do not belong, brought from mountains many miles away. These travelers are called erratics. Some sit alone in pastures, and people once thought they had been placed there by giants or carried by floods. The truth is gentler. The ice carried them, set them down, and quietly went away. How much of a mountain can a glacier carve? That question is still being studied. Some researchers think glaciers do most of the work in shaping the highest ranges. Others think rivers and landslides do more. The balance probably shifts from place to place and from one age to another, depending on the climate. The open question is how to weigh these forces against each other. The rocks remember, but they do not always tell us in a clear voice. There is something soothing about a glacier when you think of it this way. It is enormous, ancient, and almost silent. It works without hurry. It does not notice us, and it does not need to. It simply moves, grinds, polishes, and carries, season after season, century after century. Beneath the white surface there is a slow blue heart, and somewhere far below that, a stone being patiently sculpted into a shape no one has yet seen. The glacier knows what it is making. We are only beginning to learn how to read its quiet handwriting on the mountains. In the long story of how we came to understand mountains, one shape kept troubling the people who studied them. It was the flat-topped peak. A mountain, by every reasonable expectation, should rise to a ridge or a point. Wind and rain and ice should carve it into something sharp. And yet, in many corners of the world, travelers found mountains whose tops were as level as a table. The early explorers who wandered into the highlands of South America saw them clearly. In the rainforests of Venezuela and Guyana, vast cliffs of stone rose straight up from the green canopy, and their summits stretched flat for miles. The local people had known about these tabletop mountains for ages. They called them tepuis, a word from the Pemen language meaning house of the gods. To the eye of a European mapmaker in the 1800s, they made no sense at all. The first scientific accounts came slowly. Surveyors with brass instruments and leather notebooks tried to measure the heights and angles. They sketched the cliffs in careful pen and ink. They wrote letters home describing islands of rock floating above the forest, with waterfalls pouring off their flat edges into mist. The geologists who read those letters argued for decades about what the flat tops could mean. One early idea was that the summits were simply the remains of an old, lost surface. A long time ago, the thinking went, the land here was one wide plateau. Then rivers cut down through it, slicing away the softer ground and leaving only the hardest patches behind. The flat tops were the ghosts of that ancient plain, lifted high by the slow shrugging of the crust. It was a tidy theory. It also raised more questions than it answered. A second idea took shape when geologists learned how to read the layers in the stone. The tepuis are made of a tough sandstone, laid down by quiet seas almost 2 billion years ago. That makes them among the oldest exposed rocks on the planet. Some researchers wondered if the flat shape came from the way that sandstone breaks. Tough flat layers, the thinking went, would resist weathering across their wide surface and crumble only at the edges. The summit would stay level because the rock itself wanted to stay level. Both ideas had something to recommend them. Neither one fully explained the strange, isolated arrangement of the peaks, or why so many of them stood at roughly the same height. The question remained open into the 20th century, and in many ways it remains open still. Other flat-topped mountains turned up elsewhere. In the American West, travelers in covered wagons crossed mesas and buttes whose tops were also surprisingly level. In southern Africa, the famous table-shaped mountain above Cape Town drew sailors and naturalists for centuries. Each one had its own story written in its layers. Each one hinted that flatness at altitude was not a quirk but a pattern. The instruments used to study these peaks changed over time. Early surveyors relied on the theodolite, a small telescope mounted on a tripod that could measure angles with great care. With it they could work out heights and slopes from many miles away. Later, the barometer let scientists estimate elevation by measuring the weight of the air. Then came aerial photography from balloons and small planes, which gave the first true overhead views. It's only in our own age, with satellites and radar mapping, have we begun to see the full shape of these tabletop worlds. Each new tool revealed something the older ones had missed. Aerial photographs showed cracks and sinkholes invisible from the ground. Radar pierced the clouds that often hide the summits. Chemical dating of the rock samples gave numbers that surprised even the scientists who collected them. The tepuis, it turned out, were far older than anyone had guessed, and they had been eroding for so long that the human mind struggled to hold the timescale. Still, the central puzzle has not closed. Why do these particular mountains end in tables rather than peaks? Why do so many sit at similar heights? How much of their flatness comes from the rock itself, and how much from a vanished landscape we can no longer see? The answers seem to depend on which mountain you ask, and which scientist you trust, and which decade you happen to study them in. So the flat-topped mountains remain teachers of a quiet kind. They show us how slowly knowledge gathers, and how often a single strange shape can keep a question alive across many lifetimes. The instruments grow finer, the maps grow sharper, and the tables of stone still sit above the forest, holding their old silence in the morning light. Some mountains began their lives as islands. That is one of the stranger truths the rocks have whispered to us, and it is still not fully understood. Picture a small piece of land floating in a wide blue sea, far from any continent. A volcano, perhaps, or a shallow shelf crowded with coral. It sits there for millions of years alone. And then, very slowly, the plate beneath it begins to drift. It carries the little island toward a distant shore. In time, the island arrives. It cannot sink. It is too light, too thick, too stubborn. So it crashes softly into the edge of a continent and becomes part of it. The island is no longer an island. It is a mountain. Geologists have a quiet word for these wanderers. They call them terrains. Not terrain with an I, but terrain with an E, a block of crust that came from somewhere else. When you stand on certain mountains in western North America, you may be standing on rock that was once an island near the equator. The fossils in that rock do not match the fossils nearby. The minerals tell a different story. The magnetic grains inside the stone, which lock in the direction of the Earth's poles at the moment the rock cools, point to a latitude far away. Each terrain carries a memory of a homeland it has long since left behind. How many of these traveling pieces make up the mountains we see today? That is one of the open questions. Along the western edge of North America, researchers have mapped dozens of terrains, stitched together like patches on an old quilt. Some are small, some are larger than entire countries. The Cascades, parts of the Rockies, much of Alaska, all of them seem to be built, at least in part, from islands that drifted in from the ancient Pacific. But the exact paths these islands took remain hard to trace. The ocean that carried them is gone. The plate that drove them has been swallowed back into the deep earth. Only the stranded rock remains, holding clues that scientists are still learning to read. The idea itself only became widely accepted in the late 20th century. Before that, geologists puzzled over odd mismatches in the rock. A limestone full of warm water fossils would sit beside cold water shales. Volcanic rocks of one age would be wedged next to ancient seafloor of another. The simplest explanation, in the end, was the strangest. The rocks had not formed where they now sat. They had traveled, they had collided, they had stuck. Some of these traveling islands were born as volcanoes rising from the deep. Their flanks were soft with ash and pillow lava, that round, lumpy stone that forms when hot magma meets cold seawater. Others were flat coral platforms, sun-warmed and shallow, full of slow-moving creatures and bright green algae. When they slammed into a continent, they did not stay flat. The collision squeezed them, bent them, lifted them. A reef that once swayed in tropical currents now sits frozen near a snowy peak. You can find coral fossils on mountainsides in many parts of the world, sometimes thousands of feet above the nearest sea. The truly strange part is the timing. Some of these islands took 100 million years to make their crossing. The journey was slower than the rise and fall of entire dynasties of life. Dinosaurs came and went while a single terrain drifted toward its destiny. By the time it arrived, the world that had birthed it no longer existed. The volcano that built it had gone cold. The shallow sea around it had vanished. It came ashore as an orphan, carrying the geology of a lost place. One open question is how cleanly these collisions happened. Did the islands always slide gently into the continent, or did some break apart and scatter their pieces along the coast for thousands of miles? The rock record suggests both. There are terrains whose edges seem clean, almost surgical. There are others that appear to be smeared along great lengths of crust, like clay pressed sideways by a thumb. Why some glided in whole while others crumbled is a puzzle researchers are still untangling. It is a soft and quiet thought to carry into sleep. Some mountain you might one day climb may be standing on the bones of a tropical island that vanished long before the first humans walked the earth. The peak above you is not only stone, it is a traveler. It crossed an ocean that no longer exists, carried by a current that left no foam, and came to rest in a place it had never seen. And there it waits, holding its old secrets, while the world above it keeps slowly turning. Beneath the waves, far below the reach of sunlight, there is a mountain range so long it wraps around the entire planet. It runs for more than 40,000 miles, winding between the continents like a seam stitched into the floor of the sea. We call it the mid-ocean ridge, and most of it has never been seen by human eyes. It is the largest single feature on Earth, and yet for most of human history, no one knew it was there. The ridge is where the seafloor is being born. Hot rock rises slowly from deep inside the planet and pushes up through long cracks in the ocean crust. As it cools, it hardens into fresh stone, and the two sides of the crack drift gently apart. New seafloor spreads outward, year after year, at about the speed your fingernails grow. The mountains rise where this slow birth is happening, and they connect every ocean basin into one long, hidden chain. What makes this range so strange is how quietly it shapes the world above. The same forces that build these underwater peaks also push the continents apart. South America and Africa, once joined, now drift away from each other a few centimeters each year, because the mid-Atlantic ridge keeps pumping new stone between them. The mountains beneath the sea are, in a real sense, the engines that arrange the dry land we walk on. Every desert, every plain, every coastline owes some part of its shape to a ridge no one can see. The connections run deeper still. Along these underwater mountains, hot water rises through chimneys of dark mineral, glowing faintly in the black. Whole communities of strange life gather there, pale crabs, tube worms, blind shrimp, feeding not on sunlight but on the chemistry of the earth itself. Some researchers wonder whether life on our planet may have first stirred near vents like these, in the warm crevices of an ancient ridge. The question remains open. The evidence is suggestive, not certain. But it hints that the same slow forces that build mountains may also have helped build us. The ridges also speak to the climate. As fresh rock pours out along the seams of the ocean, it reacts with seawater in ways that change the chemistry of the sea over millions of years. Carbon dioxide locks into new minerals. Heat moves from the deep earth into the water. The ocean carries that heat across the globe in great slow currents, and those currents shape the weather on every continent. The mountains below the waves help set the temperature of the air above the land. They are part of a single breathing system, even though they sit hidden in the dark. How tall are they really? In places, the mid-ocean ridge rises more than 2 miles above the surrounding seafloor. If you could drain the oceans away, you would see a mountain chain dwarfing the Alps, snaking across the planet in long, gentle curves. A few of its peaks even break the surface as islands. Iceland is one of them, a piece of the mid-Atlantic ridge that grew tall enough to stand in the open air. Walk across Iceland, and you are walking along the top of an underwater mountain, with one foot on a slowly parting plate and the other on its sibling, drifting the other way. What we still do not understand is why the ridges behave so differently from place to place. In some stretches, the seafloor spreads quickly, and the mountains are low and broad. In other stretches, it spreads slowly, and the peaks rise sharp and steep, with deep valleys running down their middles. One theory points to differences in how hot the rising rock is. Another points to how thick the surrounding crust happens to be. A third suggests that older scars in the deep earth guide where new ridges form. The full answer has not yet arrived. There is also a quieter question. The ridges connect, but they do not connect everything. Some sections end abruptly. Others jog sideways along long fractures that cross the seafloor like the rungs of a ladder. Why the pattern takes this shape, no one has fully explained. The map of the deep ocean still holds many blank places, and the mountains there still keep their secrets. So when you picture the mountains of the world tonight, picture more than the ones rising into clouds. Picture the longer chain below, glowing faintly in the dark, joining every sea, shaping every shore, breathing slowly with the planet itself. The ridge is the great hidden spine of the earth, and we are only beginning to learn its song. Far beneath the white silence of Antarctica, a great mountain range lies hidden under the ice. It is called the Gamburtsev Range. It stretches for about 1,200 kilometers across the heart of the continent. Its tallest peaks rise nearly 3,000 meters above the rock below them, and yet no human eye has ever seen them. They are buried beneath more than a mile of cold, slow-moving ice. The mystery of these mountains is one of the strangest in all of geology. They are roughly the size and shape of the European Alps. They have sharp ridges, deep valleys, and steep slopes. They look young, yet by every careful measurement, they appear to be very, very old. Some studies suggest the rock itself may be over 1 billion years in age. How can mountains that old still have such sharp, jagged shapes? Time should have worn them down long ago. Scientists have only been able to study them through indirect means. Planes fly slowly across the white surface, sending sound and radar waves down through the ice. The echoes return as faint signals. From those signals, researchers build quiet maps of the hidden land below. Each flight adds a little more shape to the picture. Each pass reveals another ridge, another valley, another silent peak that no one will ever climb. One theory suggests the Gamburtsevs began their life over 1 billion years ago when ancient continents pressed together. After that first uplift, they slowly wore down. Then, much later, something woke them again. Perhaps deep heat rose from the mantle. Perhaps the crust below them grew thick and buoyant, lifting the surface like a slow tide. Some researchers wonder if rifting nearby helped push them upward a second time, around 250 million years ago. Others believe the answer lies deeper still, in roots of cold rock hanging far below the surface. The ice itself may have protected them. Around 34 million years ago, Antarctica began to freeze. A thick blanket of ice spread across the land. Once that ice settled, the usual sculptors of mountains slowed almost to a stop. Rivers no longer carved their valleys. Rain no longer washed their slopes. Wind could not reach them through the frozen shield. The mountains became a kind of fossil, locked in place, waiting in the dark. This is one of the most intriguing ideas in the whole story. The ice, which seems so destructive, may also be a great preserver. It can grind. It can polish, but once it grows thick and stable, it can also shelter the land beneath it from the slow erosion of the open sky. The Gamburtsevs may be among the best preserved old mountains anywhere on Earth. They are not crumbling, they are simply sleeping. Even so, the ice above them is changing. The vast sheet that covers Antarctica is not still. It flows outward toward the sea, slow as syrup, carrying its weight along ancient valleys. In some places, it moves faster than others. As the climate shifts, the patterns of this flow shift as well. Some parts of the ice grow thinner, other parts hold steady. The hidden mountains feel these changes too, in small ways. The pressure on their old rock rises and falls across the long ages. There are other forgotten ranges down there as well. The Transantarctic Mountains cut across the continent for thousands of kilometers, partly buried, partly exposed. Hidden basins lie between high ridges. Deep valleys, carved long before the ice arrived, still hold the shape of rivers that have not flowed in tens of millions of years. The whole interior of Antarctica is a frozen museum of older worlds. What might these mountains tell us if we could uncover them? They may hold fossils from a time when Antarctica was warm and green. They may carry the marks of ancient rivers, the shapes of old coastlines, the records of climates we barely understand. They may even hold clues about how supercontinents pulled apart long before the present map of the world took form. For now, the Gamburtsevs remain one of the great unseen places on this planet. We know roughly where they are. We can sketch their shapes from echoes in the ice, but we cannot touch them. We cannot stand on their summits. We cannot study their rock face to face. They are a range of mountains held in a kind of suspended quiet, beyond the reach of our hands and our feet, and so the question stays open. How did mountains so old keep their sharp young shapes for so long? The ice keeps its secret well. Somewhere beneath that endless white surface, the peaks wait, dreaming through the slow centuries, as patient as stone has ever been. There is a kind of mountain that does not wait for plates to crash. It rises from below, lifted by a slow plume of heat that seems to come from somewhere very deep inside the earth. These places are called hot spots, and they glow in ways that other mountains never do. The light that pours from them tells a story we still do not fully understand. Think of the Hawaiian Islands, sitting alone in the middle of the Pacific. They are not near the edge of any plate. They are not where two pieces of crust are grinding together. And yet they are mountains, tall ones, with their feet planted on the dark ocean floor and their heads lifted into the warm sky. Something pushed them up from underneath, something that still pushes today. When a hot spot vents at the surface, the world fills with a strange and ancient light. Fresh lava glows orange and gold, sometimes a deep cherry red, sometimes almost white where it is hottest. It moves in slow ribbons, cooling at the edges into a black crust while the center still shines. At night, you can see this light from far away, a soft pulse on the horizon, like a candle burning under the skin of the planet. The light of a hot spot is the light of the deep earth made visible. Most of what lies beneath our feet is hidden from us. It is locked away under miles of rock, hot and pressed and quiet. But at a hot spot, a thin column of that hidden material rises, melts as the pressure drops, and finally breaks through. For a moment, the inside of the earth glows in open air. Then it cools, hardens, and joins the slow stack of stone that builds an island mountain. How these plumes form and how deep they really go is one of the open questions of modern geology. One theory says they begin near the boundary between the mantle and the outer core, almost 2,000 miles down. In this view, narrow towers of warmer rock rise like wax in a lava lamp, slow and patient, taking tens of millions of years to reach the surface. Another theory says the plumes are shallower, born in the upper mantle, fed by smaller pockets of heat. A third group of researchers wonders if some hot spots are not plumes at all, but cracks in the plate that simply let melted rock leak through. The evidence is still being gathered, and the debate is gentle but unresolved. What we can see clearly is the trail these mountains leave behind. As a plate drifts slowly over a hot spot, new volcanoes form one after another. The older ones cool, sink, and fade, while the newer ones glow with fresh fire. The Hawaiian chain stretches across the Pacific in just this way, a long line of peaks and worn-down stumps that grows older as you travel northwest. Somewhere out there, far beneath the waves, sit the ancient ghosts of islands that once shone with the same red light. The colors of a hot spot mountain change with time. In its youth, the slopes are black and shining, made of fresh basalt still warm to the touch. Steam rises in white plumes where rain meets hot stone. Over centuries, the black weathers to brown, then to deep rust. Tiny plants find footing in the cracks, and a soft green begins to spread. Given long enough, the mountain wears a coat of forest, and the light it once made is hidden under a quiet canopy. Some hot spots burn under continents, not oceans. Beneath the wide plains of one famous national park in North America, a great pool of hot rock sits closer to the surface than almost anywhere else on land. The ground there breathes. Hot springs glow turquoise and gold from the minerals dissolved in their water. Steam catches the morning sun and turns the air pale. The mountains around this place were lifted, in part, by the heat below, and the question of whether a deep plume feeds it remains under careful study. What no one can yet say for sure is why hot spots appear where they do. Why this patch of ocean and not another? Why this corner of a continent? The Earth seems to choose its glowing places by rules we have not fully read. We see the light. We map the trails of old volcanoes. We measure the heat, and still the deeper pattern stays just out of reach, hidden in the slow, hot dark beneath the crust, waiting for someone to understand what the planet is trying to show us. If you could press your ear to the side of a mountain, you would not hear silence. You would hear a long, slow conversation. The rock would hum with tiny tremors. It would creak as the day warmed and cooled. It would whisper with water moving through hidden cracks. Mountains are not quiet things. They simply speak in a language we have to work hard to hear. Scientists place special instruments on mountainsides to listen. These tools are called seismometers, devices that pick up the smallest shivers in the ground. When the readings come back, they look like wavy lines on a screen, but those lines can be turned into sound. And when researchers play them, the mountains seem to sing. Low groans, soft pulses, a steady, slow heartbeat that rises and falls with the seasons. Some of these sounds come from far away. An earthquake on the other side of the world sends waves through the planet. Those waves pass through the deep roots of a mountain and make the whole range ring, very faintly, like a bell struck long ago. The folded rock holds onto the vibration for a while before letting it go. In this way, a mountain in one place remembers a tremor from somewhere else. Other sounds come from the mountain itself. Stone expands a little when the sun warms it. It shrinks again at night when the cold returns. This slow stretching and pulling makes the rock pop and tick, the way an old house settles after dark. On a quiet morning, climbers sometimes report hearing soft cracks coming from the cliffs around them. The mountain is shifting in its sleep. Then there is the deeper voice. Deep beneath every mountain range, the folded layers of rock carry a kind of memory. Each fold formed under pressure, millions of years ago when two pieces of crust pushed against each other. The rock bent rather than broke, and once bent, it stayed bent. Geologists can read those folds like the rings inside a tree. Each curve tells a story about a force that came and went. This is why some researchers describe folded rock as having a long memory. The shape of the rock holds the shape of an ancient push. Even after the pushing stops, even after the mountains wear down, the folds remain in the stone. A flat field today might hide tilted, twisted layers just below the soil. Those layers are echoes of a mountain that once stood there. The land forgets. The rock does not. How long can a fold hold its memory? That is one of the open questions. Some folds in very old rocks are more than 1 billion years old. They still show the curves of long-vanished mountain ranges. Yet the rock around them has been heated, squeezed, and stretched many times since then. How the original folds survived all of that without being erased is still being studied. One idea is that certain minerals lock the shape in place. Another is that the deep parts of the crust stay strong enough for long enough to keep the record. The full answer is not yet clear. The sounds mountains make are sometimes used as clues. By listening to how vibrations travel through a range, scientists can guess what lies beneath. A wave that moves quickly suggests dense, cold rock. A wave that slows down suggests something warmer, softer, perhaps partly melted. In this way, sound becomes a kind of flashlight, shining into places no drill can reach. The mountain answers back, in tones too low for human ears, and researchers translate. There are sounds that remain hard to explain. Some ranges hum at very low frequencies for reasons no one fully understands. The hum may come from ocean waves crashing on distant shores, sending energy through the crust. It may come from wind passing over the peaks. It may come from the slow grinding of plates far below. Most likely, it comes from a mix of all these things, blended into one quiet tone the planet keeps singing to itself. Imagine, then, that the mountain you are picturing tonight is not still. It is gently ringing. It is holding the memory of pushes that ended long before any person walked the earth. Its folds are old letters, written in stone, still waiting to be fully read. The wind moves across its slopes. Somewhere inside it, a wave from a far-off tremor passes through and fades away. We have only just begun to learn this language. Each new instrument hears something a little different. Each new study turns a faint sound into a clearer question. The mountains keep speaking, and we slowly are learning how to listen. For now, the long memory of folded rock keeps most of its stories to itself. There is a quiet kind of arithmetic hidden inside every mountain. It is not the math of textbooks with crisp answers at the back of the page. It is the slow math of stone, written in millions of years, in millimeters per century, in grains of sand carried downstream one storm at a time. And when researchers try to add it all up to find out how long a mountain might live, the numbers begin to drift in surprising directions. The basic equation feels simple at first. A mountain rises at some rate. Wind and water wear it down at some other rate. If the rising is faster than the wearing, the peak grows. If the wearing wins, the peak shrinks. Somewhere in between lies a strange balance, where a mountain seems to hold its height for ages, even as its body is quietly replaced from below. The measured numbers are gentle and almost beautiful. The Himalayas push upward at roughly 5 to 10 millimeters each year. That is about the thickness of a pencil. The Alps creep up by perhaps 1 or 2 millimeters in the same time. The Appalachians, far older and far quieter, barely move at all. These rates sound tiny, but stretched across 1,000,000 years they build entire skylines. Erosion has its own slow numbers. In wet, steep places, rivers and rain can strip away several millimeters of rock each year. In dry, flat places, the same amount of rock might last 100,000 years. The ratio between uplift and erosion decides everything. It decides whether a range will rise into the clouds or sink quietly back into hills. From these simple rates, scientists try to estimate the lifespan of a mountain range. The answers vary wildly. Some young ranges may live only 10 or 20 million years before erosion takes them down. Others, locked into stable continents, may keep their shape for hundreds of millions of years. The Appalachians began forming nearly 500 million years ago. They are still here, softened, rounded, but here. The open question is why some ranges last so much longer than the math seems to allow. By the simplest calculations, the Appalachians should have worn flat long ago. By the same calculations, the Urals in Russia should be gentle ridges, not the long spine of stone they remain. Something keeps lifting them, slowly, quietly, long after the original collision that built them has ended. One idea points to the deep roots beneath old mountains. As erosion strips away the top, the lighter crust floats upward, the way a boat rises when cargo is removed. This slow rebound can lift a worn range for tens of millions of years, replacing lost height from below. It is a kind of gift from the planet, a way of keeping the mountains in the sky long after their parents have stopped pushing. Another idea suggests that the mantle itself, that hot, slow-flowing layer beneath the crust, sometimes nudges old ranges back upward through currents we cannot fully map. Warm rock rises in patient plumes, lifting whole regions by a few hundred meters over millions of years. Whether this explains the stubborn height of certain ancient ranges is still being studied. There is also the question of what counts as the end of a mountain. A peak that has eroded to a rolling hill is no longer a mountain by most measures. Yet its roots deep below may still be there, ghostly outlines in the rock. Some geologists argue that a mountain never truly dies. It only changes form, leaving its memory pressed into the layers beneath, waiting for some future uplift to bring it partly back. The mathematics, then, is not really a stopwatch. It is more like a long, soft conversation between forces. Uplift speaks, erosion answers, gravity adjusts, climate shifts the tone. The mantle hums beneath everything. The result is not a single lifespan, but a range of possible lifespans, each one branching into more. And there is a quiet beauty in this uncertainty. The numbers are elegant, even when they refuse to give a final answer. A pencil width of rise each year, a whisper of erosion each storm, 500 million years of slow argument between rising stone and falling rain. The arithmetic of mountains is the arithmetic of patience. So when we ask how long a mountain lives, we are really asking how long the planet itself stays in conversation with that piece of crust. The Andes are still young, still rising, still arguing. The Appalachians are old, soft-spoken, and somehow still standing. Somewhere out there, ranges we have not yet named are stirring deep below, beginning their own slow climb. How long any of them will last, the equations cannot yet say. There is something quietly strange about a mountain that is still growing. We tend to think of peaks as finished things, carved long ago and now standing still. The truth is more delicate. Many of the great ranges of the world are rising at this very moment, lifted by forces deep below, while wind and water work just as steadily to wear them back down. A mountain is not a sculpture. It is a balance. The Himalayas, for example, are still climbing. Each year they push upward by roughly a centimeter, about the width of a fingernail. That sounds small, but over a human lifetime it adds nearly a meter of new height. The Alps rise too, though more slowly. So do parts of the Andes, the Rockies, and ranges most of us have never heard of. Across the globe, stone is quietly moving toward the sky. And yet these mountains are not, on the whole, getting taller. That is the strange part. The rate of uplift is roughly matched by the rate of wear. Rain dissolves the rock. Rivers carry the grains to the sea. Glaciers grind the high valleys. Frost cracks the cliffs apart in winter. The mountain rises, and the mountain falls at almost the same pace. The peaks we see are a kind of standing wave in stone, held up by a balance so even that it looks like stillness. Researchers find this balance remarkable and a little puzzling. One idea is that erosion and uplift are linked in a feedback loop. When a range rises higher, it catches more rain and snow, which speeds up the wearing away. As the heavy rock is stripped from the surface, the deep roots of the mountain float upward in response, like a boat that has shed its ballast. This rising root then pushes the peaks higher again, which catches more weather, which strips more stone. The cycle feeds itself. If that idea is right, then a mountain range is not just shaped by climate. It also shapes its own climate and is shaped in return. Change one part of the system and the whole thing shifts. A wetter sky could lower the peaks. A drier sky could let them grow. A small change in temperature could move the snowline up or down a few hundred meters, and with it, the place where glaciers do their patient cutting. The mountains we know are tuned to the world we have. A different world would carve different mountains. This is part of a larger fragility that scientists notice when they look at our planet as a whole. Earth sits at a distance from the sun that allows liquid water to exist on its surface. Not too close, not too far. The atmosphere is thin, only a few tens of kilometers of breathable air wrapped around a world thousands of kilometers wide. That thin shell holds the rain that wears the mountains. It holds the wind that drives the storms. It holds the warmth that lets ice melt in summer and freeze again in winter. Without it, the slow dance of uplift and erosion would not exist in the form we know. The interior of the Earth matters too. The mantle is still hot, billions of years after the planet formed, and that heat is what drives the plates. If the mantle cooled too quickly, the plates would slow, then stop, and mountain building would fade. If the heat were too great, the crust might churn so fast that no range could stand for long. Somewhere between those extremes lies the Earth we have, with its steady, slow rise of stone. Researchers do not fully understand how finely tuned this balance really is. Some wonder whether small shifts in climate over the next thousands of years will change which ranges grow and which shrink. Others ask whether the long warming and cooling cycles of the planet, stretching across millions of years, have already raised and lowered countless peaks we cannot now see. The answers depend on variables we are still learning to measure. What we can say is that the mountain outside your window, if there is one, is not as solid as it looks. It is rising and falling at the same time. It is held in place by a quiet agreement between deep heat and thin air, between rock and rain, between forces we can name and forces we are still trying to understand. Change any one of them by very much, and the agreement breaks. For tonight, the balance holds. Somewhere in the dark, snow is settling on a high ridge. A river is carrying a few grains of stone toward the sea, and the mountain, ever so slightly, is growing. Mountains do something strange. They do not just sit beneath the weather. They make it. They shape the clouds that drift around them. They steer the wind. They pull rain from the sky on one side and leave dry desert on the other. And yet, after all the years of study, much of how mountains and weather work together remains an open puzzle. The simplest part is easy to picture. Wet air rolls in from the sea. It hits the slope of a mountain and has nowhere to go but up. As it climbs, it cools. Cool air cannot hold as much water as warm air, so the water falls out as rain or as snow on the high peaks. By the time the air crosses the ridge and slides down the far side, it is dry. That far side often becomes a desert. We call this a rain shadow, and you can see it on maps all over the world. That much we understand. The deeper questions begin where the picture seems simple. How much rain falls on a slope, and exactly where, depends on countless tiny details. The shape of the ridge, the angle of the wind, the temperature of the sea hundreds of miles away, the roughness of the rock, the forests growing on the lower flanks. Even small changes in any of these can shift a storm by miles. Scientists build careful models to predict mountain weather, and the models keep getting better. But mountains still surprise us. A valley that should be dry receives a sudden flood. A peak that should catch snow stays bare. The reasons are not always clear. There is a slower question hiding underneath. Mountains do not only respond to weather. Over deep time, they help create the climate of whole continents. The slow rise of a great range can change the path of the wind across half the planet. Some researchers wonder whether the lifting of the Himalayas and the high plateau of Tibet helped cool the Earth millions of years ago. The idea is that fresh rock, exposed by uplift, weathered in the rain. That weathering pulled a gas called carbon dioxide out of the air. Less carbon dioxide meant a cooler world. It is a beautiful theory. It is also still debated. Other researchers think the cooling came mostly from other causes, and the mountains played only a small part. The reverse question is just as open. Does climate shape mountains as much as mountains shape climate? Rain and ice wear rock away. If rain falls hard on one side of a range for millions of years, that side erodes faster. The mountain loses weight there. And because mountains float on the hot, slow rock below, losing weight in one place can let the range tilt or rise in another. Some scientists believe entire mountain shapes are sculpted as much by weather as by the forces pushing them up. Others argue the deeper forces below dominate, and the weather is only a finishing touch. The honest answer seems to be that both are true at once, but no one yet knows the exact balance. Then there are the strange small mysteries. Why do some mountain ranges grow their own thunderstorms in the afternoon, day after day, in the warm months? Why do certain peaks wear a cap of cloud that almost never lifts, while a neighbor just a few miles away stands clear? Why do winds sometimes pour down a mountainside warm and dry, instead of cold, scouring the valleys with a hot breath that can melt snow in hours? These warm downslope winds have local names in many languages. We know they exist. We can describe them, but predicting exactly when they will arrive and how strong they will be still escapes us. There is also the question of the future. As the planet warms, the snow line on many mountains is creeping higher. Glaciers are shrinking. Rain is falling where snow used to fall. This changes the rivers below, the soils, the forests, the cities that depend on the slow melt of high ice for their summer water. Researchers are working hard to understand what comes next. The honest truth is that mountains are so complicated and the changes so new that the answers are still being written. So the listener can lie in the dark and picture it, a long ridge of stone holding a sky against itself. Clouds piling up on one shoulder, sunlight on the other, a wind that no one fully understands threading the high passes. Snow falling on a peak that may not see snow forever. The mountain breathing weather into the world, and the world breathing weather back into the mountain. In a slow conversation we are only beginning to overhear. Somewhere beneath your feet, or perhaps beneath the floor of a quiet ocean halfway across the world, lies the worn-down memory of a mountain range that no one will ever climb. It was tall once, maybe as tall as the Alps, maybe taller. It stood for tens of millions of years, weathered by rain and wind, polished by ice, until it slowly sank back into the slow churn of the planet. We do not know its name. We do not know its shape. We only know, from the chemistry of certain old stones, that something high once stood where now there is only flat ground. These are the lost ranges. And the strange truth is that many of them will stay lost forever. Geologists can sometimes find the ghost of an old mountain in the rocks left behind. A type of mineral called zircon, tiny and tough, can survive almost anything. When mountains erode, their zircons wash into rivers, then into seas, then into layers of mud that harden into stone. Millions of years later, those zircons whisper a faint signal about the peaks that once towered above them. From those whispers, we have learned that ancient mountain belts once crossed places that now seem flat and ordinary. Parts of Central Australia, wide stretches of Canada, the quiet middle of Africa. But the signal is faint and much of it is gone. Plate tectonics is patient and thorough. It folds old crust back into the deep mantle, recycling stone the way a river recycles sand. A mountain that lived and died 500 million years ago may have left behind only a few stubborn grains. The rest has been swallowed. One open question is how many mountain ranges Earth has actually made across its long life. Some researchers estimate dozens of major orogenies, the long, slow events that build great chains of peaks. Others suspect there may have been many more, smaller and shorter-lived, lost to time before anything could record them. The early Earth, hotter and more restless, may have grown and erased ranges in cycles we can barely picture. The first few billion years of mountain history may be almost entirely missing. Now look forward. 1,000,000 years from now, the Himalayas will still be here, though slightly changed. India keeps pushing north into Asia by a few centimeters each year, and the highest peaks will likely keep rising for a long while yet. The Alps will be a little lower. The Appalachians, already old and gentle, will be softer still. New volcanoes will have grown along the edges of the Pacific. Some islands will have joined continents. Some coasts will have drowned. 10 million years from now, the picture grows stranger. East Africa may have torn fully open, leaving a new ocean where the rift valleys lie today. The land on either side will lift into fresh highlands as the crust adjusts. Australia will have drifted further north, pressing into the islands above it, raising new ridges from the sea. 50 million years from now, the Mediterranean may close entirely as Africa keeps grinding into Europe. Where there is now blue water and quiet beaches, there may stand a new mountain range, raw and sharp, rivaling the Himalayas of our own age. Geologists already have a tentative name for this future chain in their papers, though of course no one will be there to see whether the guess holds. Look further still, and the certainty fades. 200 million years on, the continents may have gathered again into a single great landmass. Some models suggest one supercontinent. Others suggest a different arrangement entirely. Along its long suture lines, where old oceans were squeezed shut, vast mountain belts would rise. They would weather, they would fall. They would leave their own faint zircons in some future seabed, waiting to be read by minds we cannot imagine. 1 billion years from now, the sun will be hotter, the oceans thinner, the surface of the planet much changed. Yet so long as the mantle still flows, mountains will keep being born. New peaks will catch new clouds, new rivers will cut new valleys, and new ranges will, in their turn, be lost. This is perhaps the gentlest mystery of all. Not the mountains we can see, but the ones we cannot, the ones that came before any eye opened to watch them, the ones that will rise long after every human story has ended. Earth has been making and unmaking mountains for over 4 billion years, and almost none of that record remains. The rocks beneath you tonight may be the last quiet trace of a summit that once held snow under a sky no person ever saw. Step back now as far as you can. Picture the Earth from a great distance, a soft blue sphere wrapped in white cloud. From out there, the mountains barely show. The tallest peak on the planet is just a small wrinkle on the skin of a world that is itself a small stone turning in a quiet corner of space. And yet those wrinkles are made of the same matter as everything else. The same matter as the soft pillow beneath your head. The rocks that build the mountains are old. Some of them are nearly as old as the Earth itself, around 4.5 billion years. But the atoms inside those rocks are older still. The iron in a mountain's heart, the silicon in its gray cliffs, the carbon woven into its limestone, all of these were forged inside ancient stars that lived and died long before our sun was born. When those stars ended their lives, they scattered their atoms across the dark. Some of that scattered dust gathered slowly into the cloud that became our solar system. Some of it became Earth. Some of it became mountains. So when you look at a great range rising from a plain, you are looking at something that is, in a quiet sense, made of starlight that has cooled and settled and folded. The same is true of you. The calcium in your bones, the iron in your blood, the oxygen filling your lungs as you breathe slowly towards sleep. All of these atoms were once inside stars. You and the mountains share a family. You are cousins in a way, made from the same ancient material, shaped by very different forces over very different timescales. The mountain rose because plates collided. You rose because cells divided. Both processes began with stardust. Both will end in time as the atoms move on to become something else. This is one of the gentlest thoughts in all of science. Nothing in the physical world is truly lost. The atoms that make a peak today were once part of an ocean floor, and before that part of a different mountain, and before that part of a glowing cloud drifting through the early solar system. The atoms that make you today were borrowed from soil and rain and bread and air, and one day they will be borrowed back. Mountains and people are both temporary arrangements of very patient material. And still, after all that time, the rocks refuse to tell us everything. They keep their secrets close. We do not know exactly when the first mountains rose on Earth. We do not know how many ranges have come and gone before the ones we see today. We do not know what the planet's surface looked like in its deepest youth, because almost no rock from that era has survived. The Earth recycles itself, and most of its early memory is gone. We do not fully understand why some mountains keep growing while others give up. We do not know why certain old ranges stand stubbornly above the plains long after they should have worn flat. We do not know how mountains and rain and ice trade influence over millions of years, each one shaping the others in ways we are only beginning to map. The questions are layered, like the rocks themselves. Maybe that is the kindest thing about this whole subject. The mystery is not frightening, it is patient, it waits. It does not need to be solved tonight or in our lifetime or in the next 1,000 lifetimes. The mountains will keep rising and wearing down whether we understand them or not. The earth will keep folding its skin into new shapes. The stars will keep aging in their slow furnaces, sending new atoms outward into the long dark, where one day they may gather into new worlds and new ranges and new beings who look up at their own peaks and wonder. You are part of that long, slow story. The breath moving in and out of your chest right now is borrowed from the same air that has flowed around mountains for billions of years. The water in your body has been in glaciers, in rivers, in clouds passing over high stone summits. You are not separate from the mountains. You are made of the same material, sharing the same brief moment of arrangement, taking part in the same enormous and unfinished story. There is something restful in knowing that. The mountains do not hurry. The atoms do not worry. The mystery is allowed to remain open. And on this quiet night, with the world turning slowly beneath you, it is enough simply to belong to all of it and to rest. And so we come to the quiet end of our long walk among the mountains. The facts are spoken. The questions are still open as they should be. The peaks remain where they have always been, lifting and falling in their slow, patient way, far older than any of us, far younger than the stone they are made from. Picture the earth from a great distance, a small blue and white sphere turning gently in the dark. From that far away, the tallest mountains are only the softest wrinkles on a smooth, round skin. The Himalayas, the Andes, the Alps, the Rockies, all of them flatten into faint creases. The deep ocean trenches vanish into shadow. The whole planet looks like a single calm marble, glowing in soft sunlight, half in day and half in night. Now picture the night side, a great curve of darkness, lit only by the pale silver of the moon. Below that moonlight, the oceans rest. Their surfaces rise and fall in long, slow swells. Somewhere far beneath, the underwater ranges sleep in total black, their basalt slopes never touched by light. The water above them is cold and quiet and deep. Now picture the great mountain ranges in that same gentle darkness. Snow on the high passes glows faintly under the stars. Glaciers creak softly as they shift, grain by grain, down their stone valleys. A pebble loosens somewhere on a ridge and tumbles a few feet before stopping. A small stream of meltwater finds a new path between two rocks. These tiny motions are the breathing of a mountain. They are so slow that no one is awake to hear them. In the foothills, forests rest beneath a thin mist. Owls drift between the pines. A fox moves quietly along a familiar trail. The trees stand in their long rows up the slopes, growing one slow ring at a time. Above the tree line, the land turns to bare stone and lichen and patches of old snow. Higher still, only ice and wind and silence. The summit of any great peak at night is one of the calmest places on Earth. And below all of it, deep underground, the roots of the mountains press into the soft mantle. The crust floats on that warm, slow-flowing rock like a raft on thick honey. As erosion strips a peak from above, the root rises a little to balance the loss. As collision lifts a range from below, the root sinks deeper to match. This quiet exchange has been happening for billions of years. It is happening now, beneath your feet, beneath your bed, beneath the soft pillow under your head. You are resting on a planet that is always moving, very slowly, in ways you cannot feel. Plates drift the width of a fingernail each year. Mountains grow the thickness of a sheet of paper. Rivers carry one grain of sand at a time toward the sea. Over millions of years, these small motions build whole ranges and wear them back down to soft hills. Over billions of years, they rearrange the face of the world. There is something kind in that slowness. It means the ground beneath you is patient. It means the mountains you have known your whole life will still be there tomorrow, almost exactly the same. It means the questions we ask tonight about how peaks rise, how they fall, what hides in their roots, whether they shape, what ranges may still wait undiscovered under ice or sea, these questions can keep. They are not in a hurry. They have waited a long time. They will wait a little longer. So let your thoughts settle now, the way fine dust settles on a windless ledge. Let the worries of the day drift down the slope and away. The earth is turning gently in the dark. The moon is keeping its quiet watch over the oceans. The mountains are doing what they have always done, lifting and folding and weathering and resting, one slow heartbeat at a time. You are small and the planet is large, and that is a comforting thing. You are held by gravity, and gravity is the same force that shapes the highest peaks. The same patience that built the Himalayas is in the breath rising and falling in your chest. The same calm that lives on a snowy summit at midnight is here in this room with you now. Sleep well. The mountains will stand watch. The stars will keep their slow turning. And tomorrow, when you wake, the Earth will still be here, still wondering with us, still keeping its beautiful secrets. Subscribe for a brand new Earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.